Imagine you grab a small generator and you pull a wire from the hot slot of its outlet. You drive the other end deep into the soil. You fire up the machine. It hums, but nothing happens. No spark, no current rushing into the earth. Why not? Is the ground an insulator, or is something else going on? The secret lies in what we call the illusion of ground. What makes a power line that's fallen on the ground throw off sparks and arcs of fire, while your little generator, connected to that same ground, does absolutely nothing? And why can lightning move millions of amps in an instant, but your small generator stays trapped in its own quiet loop? This is the mystery we're going to unravel today. Get ready, because this story is going to change the way you look at power forever. If you like this content, don't forget to hit that like button and subscribe to the channel. When we talk about electricity, we picture wires carrying neat streams of current, always forming a closed loop. But that image is only part of the truth. A circuit is really just a way to describe how charges move in response to differences in potential. The ground beneath us isn't automatically part of that picture. Think about a battery. If you press one terminal into the soil, nothing dramatic happens. The soil doesn't just suck charge away because there's no return path for it. And yet, when a power line falls to the earth, sparks leap and arcs form. The difference isn't in the earth itself, but in the way the entire system is tied together. Lightning offers another contrast. A massive imbalance of charges builds between the clouds and the earth until the air itself just breaks down, creating a sudden path. Millions of amps flow in an instant. But your little generator, wired to a lonely ground rod, has no such imbalance. There is energy stored in its coils, but without a complete path, that energy just stays trapped, humming quietly inside its own loop. Ground as a reference point. In a lot of small devices, the word ground doesn't mean the dirt under our feet at all. It simply marks a shared reference point for measuring voltages. On a circuit board inside a toy or a radio, one trace is labeled ground, even though it has no connection to the actual earth. It's just chosen as 0 volts to make calculations easier. Voltage is always about comparison. You can't talk about a single point having voltage all on its own. It has to be compared to something else. By convention, we just call one spot 0, and then we measure everything else relative to it. And that's why two identical circuits can both claim to be grounded, even if one is sitting on your desk and the other is floating on a satellite. For low-voltage electronics, whether the circuit touches the actual earth hardly even matters. The difference in potential between a few volts on a chip and the enormous size of the planet is insignificant. But as voltages rise and systems connect across long distances, that choice of reference becomes critical. That's where the earth starts to play a much more active role. Now imagine stepping up from a small toy to the vast machinery of the power grid. At the heart of it all sits the generator. Inside, magnets spin past heavy coils of wire, pushing currents into conductors that feed entire cities. Most systems produce 3 separate streams called phases, which together form the backbone of transmission. If you look up at high-voltage lines, you often see 3 thick cables running side by side. Those are the phases. Each carries a current that rises and falls in a rhythm, offset from the others, so the load stays balanced. What you don't see is a 4th cable running to the ground. The link between these phases in the earth is a lot weaker than you might expect. That link comes from something called capacitive coupling. Even when they're not connected, any conductor sitting near the ground develops a faint relationship with it, like 2 plates of a capacitor. This invisible bond keeps the phase voltages hovering in balance with respect to the earth, but it's fragile. Under normal operation, it holds steady enough. But when a disturbance comes, like a fallen branch brushing a line, that delicate balance is pushed aside, and the true role of grounding begins to show itself. Faults in an ungrounded world. Picture what happens when one of those three phases touches the earth in a system without a firm ground connection. Maybe a line breaks loose in the wind and rests against wet soil, or a conductor brushes against the steel of a tower. At that instant, one phase is tied directly to the ground. Surprisingly, the system doesn't collapse. Motors keep spinning, lights stay on, and the other two phases continue to supply power. That's because the loads are connected between phases, not between a phase and the earth. To them, little has changed. This is one advantage of leaving a system ungrounded. It can ride through a single fault without shutting down. But the picture has a darker side. With one phase pinned to ground, the other two are forced upward in potential. Their voltage to earth nearly doubles. That might not bother the equipment immediately, but it demands heavier insulation, taller towers, and greater clearances. Costs grow and risks mount. So while an ungrounded system might look resilient, it's hiding danger. The imbalance pushes stress into every cable, every transformer, every insulator. It buys time during a fault, but at the price of higher strain waiting quietly in the background. Why current needs a path. Protective devices can't act without the movement of current. Every fuse, every breaker, every relay looks for a surge that signals trouble. If no extra current flows, the problem can just remain hidden. That's why grounding becomes more than just a formality. It creates a path that allows faults to reveal themselves. Think about a simple toaster. Under normal use, electricity runs from the hot conductor through the heating element and back along the neutral. The loop is complete. But if a wire inside comes loose and touches the metal shell, the case itself can become energized. Without a safe outlet, it just sits there waiting for someone's hand. You touch it, and you become the missing return path. The solution is a deliberate bond, a grounding wire tied to the case and back to the neutral. When the fault occurs, current rushes down this low-resistance path instead of through you. The surge is large enough to trip the breaker. The same principle scales up to the grid. Substations and towers connect to the earth so that when a fault strikes, a river of current can flow. Relays sense it instantly and cut the line. Without that deliberate connection, danger can remain invisible. The earth as a conductor. To see what kind of conductor the earth really is, imagine pressing two copper rods into a box of dry sand and wiring them through a light bulb. Flip the switch, and nothing glows. The sand resists the flow way too strongly. Even when water is poured in, only the faintest current creeps through. Soil just doesn't behave like copper. Its ability to carry a charge depends on minerals, moisture, and temperature. Add a little salt to the water, and suddenly the bulb glimmers, because the ions give the current a way forward. That's why grounding systems vary so much from place to place. Clay, rock, and sand each respond differently. When current leaks into the soil, it doesn't travel as a single stream. Instead, it spreads outward in every direction, forming shells of decreasing potential. Close to the rod, the drop is steep, but farther out, it levels until the current just vanishes into the vastness of the earth. This spreading nature makes soil a poor wire, and yet its size gives it power. It's both resistance and infinity all at once. Potentials that harm. When current spreads through the ground, the voltage at each point isn't the same. A single step across the soil can place your feet at two different potentials. Your body, way more conductive than rock or sand, can become the bridge. Current rises through one leg and exits the other. This is called step potential, and it's taken lives in an instant. There's also touch potential. Imagine placing a hand on a metal frame that has fault current flowing into the ground. Your feet stand on soil at one voltage, while your hand rests on steel at another. The difference drives current across your chest. To